The advent of the four-engine bomber marked a revolutionary leap in military aviation, transforming the scale and scope of air warfare. The B-17 Flying Fortress was the symbol of this technological might. A vast, complex machine designed to carry destruction deep into enemy territory, flying at altitudes once considered untouchable by human pilots or enemy aircraft. It was precisely this capability, the ability to ascend to over 30,000 feet, that became both its greatest advantage and its most profound vulnerability. At these extreme altitudes, the air becomes a hostile, alien environment. Temperatures plummet to -50 degrees Fahrenheit, and the atmospheric pressure drops to levels where human survival is measured in mere minutes without assistance. To conquer this lethal environment, the B-17 relied on a sophisticated, pressurized oxygen system, a delicate network of tanks, regulators, and tubing designed to be the crew's lifeline. Without this system functioning flawlessly, the entire air superiority strategy collapsed. The crew would swiftly succumb to the silent, invisible killer known as anoxia, or oxygen deprivation. The Air Corps entered the war with profound, if misplaced, confidence in this system. The regulations were clear, the maintenance protocols were stringent, and the design, they believed, was robust. Yet, almost from the start of serious high-altitude bombing raids over Europe in late 1942, a series of mysterious, tragic incidents began to plague the crews. These were not losses due to flak or the aggressive interceptors of the Luftwaffe. These were internal disasters. Gunners found slumped over their weapons, navigators collapsing over their charts, and co-pilots failing to respond to radio checks. The symptoms were chillingly uniform: confusion, irrationality, followed by swift unconsciousness and often death. The initial official response was one of immediate suspicion directed at the crews themselves. Investigators theorized poor training, operator error, or perhaps even a failure of morale. The idea that a meticulously engineered life support system could be failing systemically under operational stress was deemed improbable, almost bordering on professional heresy. The institution preferred to believe in the flaw of man over the flaw of the machine. This denial masked a burgeoning crisis that was costing the 8th Air Force experienced airmen faster than enemy combat could account for. The losses were insidious, often occurring mid-mission, leaving the remaining crew members scrambling to revive their comrades, while simultaneously navigating flak and evasive maneuvers. The fear among the bomber crews was palpable, a chilling anxiety that their true enemy was not the German air defense, but the frigid, rarefied air inside their own aircraft. The design of the oxygen masks and the regulators were subjected to immediate cursory reviews, but the deeper problem remained undiscovered because the official tests were never conducted under the exact, sustained, high-altitude cold conditions of a typical 8-hour European mission. The operational environment was the true stress test, one the system was failing dramatically. The stage was set for a desperate, unauthorized investigation by the very men whose lives depended on uncovering the lethal, technical secret hidden within the B-17's lifeline. This silent killer, the flaw within the oxygen system, would prove to be a problem of bureaucratic arrogance, compounded by an engineering oversight of microscopic scale but catastrophic consequence. The Air Corps had conquered the altitude, but they were tragically unprepared for the engineering challenges of survival at those heights. The high-altitude environment in which the B-17 operated was one of relentless, brutal cold, a factor that engineers had conceptually acknowledged but fatally underestimated in the design of the life support systems. At 30,000 feet, where the bombers flew to evade the most accurate anti-aircraft artillery, the outside air temperature routinely dropped below -40 degrees and often approached -60. This cold, combined with the presence of moisture exhaled by the crew, introduced by leaky seals or naturally present in the system, created the perfect conditions for a systemic failure. The initial symptoms of oxygen deprivation were often missed by the crews themselves, adding a layer of cruel irony to the tragedy. Anoxia manifests not as choking or gasping, but as a subtle, creeping euphoria, followed by impaired judgment, tunnel vision, and then sudden, profound unconsciousness. Gunners, focused intensely on the threat of the Luftwaffe, often failed to realize they were victims until they were unable to move their fingers or communicate with the flight deck. The key component at the heart of this life support network was the oxygen regulator, a complex device designed to precisely mix ambient air with pure oxygen from the storage tanks, adjusting the ratio based on the aircraft's current altitude. The regulator was the gatekeeper of life, and it was here that the insidious flaw lay hidden. The primary model in use was the Type A14 regulator, a robust, sophisticated device that performed flawlessly in the controlled temperatures of the laboratory. However, the A14 was highly susceptible to freezing. The moisture present in the system, even trace amounts condensing from the crew's breath, would accumulate near the critical valves and mechanisms within the regulator. Once the aircraft reached the sustained, deep cold of cruising altitude, this moisture would freeze solid, either completely blocking the oxygen flow or jamming the regulator valve open or shut. The most frequent failure mode was a slow, partial blockage that restricted flow, leading to the gradual, silent onset of anoxia. The condition, often mistaken for simple exhaustion or lack of training. The systemic nature of this failure created widespread, yet hard-to-diagnose, intermittent casualties across the 8th Air Force. Crews who flew one mission without incident might lose 2 men on the next, creating a pattern of seemingly random fatalities that terrified the airmen. The initial lack of external damage made investigations inconclusive. The men simply drifted off. The medical officers, initially focused on carbon monoxide poisoning or pilot error, struggled to link the seemingly disparate cases to a single engineering cause. The tragedy deepened because the very conditions that triggered the regulator's failure, sustained deep cold at high altitude, were precisely the conditions that could not be easily replicated in the standard training and testing facilities used by the Air Technical Service Command, ATSC. The testing facilities were fundamentally inadequate to simulate the 8-hour exposure to lethal temperatures that a crew endured over a typical European target run. This engineering oversight, rooted in inadequate pre-war testing protocols, ensured that the crisis would continue to deepen until the voices of the combat crews themselves could no longer be ignored. The realization that their own life support system was failing them under the most critical conditions introduced a new, profound level of psychological warfare into the already fraught lives of the B-17 airmen. The crisis of the silent killer quickly escalated from a medical puzzle to a profound institutional failure, rooted in bureaucratic inertia and professional pride. As reports of unexplained crew collapses and fatalities mounted, the official response from the Air Technical Service Command, ATSC, was one of entrenched denial. The engineers who designed the Type A14 regulator were highly confident in their product, which had passed all standard tests conducted within the warm, predictable environment of the test facility. They summarily dismissed the combat reports as anecdotal, attributing the casualties to human factors: fatigue, inadequate pre-flight checks, or most damagingly, insufficient crew training. The idea that a meticulously designed piece of American technology could be fundamentally flawed was considered politically and professionally untenable. This institutional stubbornness created a perilous chasm between the command structure and the fighting crews. Subordinates attempting to report the systemic nature of the oxygen failures often found their reports minimized, ignored, or actively suppressed. The Air Corps was deeply invested in maintaining the narrative of technological infallibility, and the oxygen crisis threatened to expose a critical weakness at the heart of the strategic bombing campaign. However, The sheer volume of unexplained losses eventually compelled a few determined individuals to challenge the official narrative. These were often medical officers or junior technical personnel who began conducting unauthorized, makeshift investigations in the field. Lacking specialized cold weather testing facilities, these resourceful investigators utilized simple, empirical methods. They placed working A-14 regulators outside the relative warmth of the fuselage, often in the exposed tail sections or in unheated bomb bays, to simulate the sustained, deep cold of the cruising altitude. The results were terrifyingly consistent. After several hours, the regulators invariably failed to deliver the required oxygen flow, freezing solid due to accumulated moisture. These field tests, though technically rudimentary, provided the first undeniable, objective proof that the A-14 regulator itself was the mechanical culprit. The official denial began to crumble not because of a grand scientific discovery, but because of the persistent, high-stakes efforts of junior officers who risked their careers to prove that the equipment was broken. The crucial step was linking the freezing regulator to the lack of oxygen flow. They discovered that a critical valve within the regulator, designed to manage the oxygen pressure, was prone to having moisture condense on its seat. Once frozen, this valve would either stick in a partially closed position, starving the crew of oxygen, or, in catastrophic cases, freeze entirely, cutting off the lifeline. The tragedy was further underscored by the fact that the solution was mechanically simple. A slight redesign of the valve seat and the incorporation of a simple anti-icing heating element or drying agent within the system could have prevented the entire crisis. The delay in implementing this simple fix, caused by institutional arrogance and denial, cost the lives of hundreds of highly trained airmen and severely hampered the operational effectiveness of the 8th Air Force during a crucial phase of the war. The crisis revealed that the deadliest enemies were sometimes found within the very system designed to protect the fighting men. The realization that the Type A-14 regulator was the source of the silent killer instigated a desperate, unauthorized campaign by junior officers and maintenance crews in the field to protect their men. Lacking official support for a redesign, these resourceful personnel implemented makeshift, non-standard solutions, operating outside the established maintenance protocols. This grassroots effort reflected a profound lack of faith in the ATSC and a determination to prioritize the lives of the crews over bureaucratic regulations. One of the most common improvised solutions involved the rigorous, frequent application of small amounts of a non-freezing agent, such as alcohol, directly into the regulator's critical valves before and sometimes during missions. This was a dangerous procedure, as it risked contaminating the oxygen supply, but it was viewed as a necessary evil to displace the moisture and prevent the catastrophic freeze-up. Maintenance crews also began focusing intensely on the purity of the oxygen supply itself, implementing their own drying procedures and adding extra filtration to the storage tanks. Despite the fact that these measures were officially deemed unnecessary by the command, the true fix, however, lay in understanding the thermodynamic chain reaction that caused the freeze. As the high-pressure oxygen was released from the tanks and passed through the regulator to be mixed with cabin air, the rapid pressure drop caused a corresponding and dramatic temperature drop. This sudden, intense cooling exacerbated the problem of moisture condensation around the valve seats, pushing the system past the freezing point. The engineers who finally got permission to investigate utilized sophisticated and often secretly acquired thermocouples and pressure gauges to measure the temperatures inside the regulator under actual high-altitude conditions. Their data confirmed the unauthorized field tests. The local temperature drop within the A-14 was sufficient to solidify any residual moisture. This confirmation finally provided the technical ammunition needed to confront the highest levels of the ATSC. The institutional battle was long and arduous. It required the intervention of high-ranking combat commanders who personally witnessed the casualties and were willing to risk the political fallout of openly contradicting the engineering command. The weight of evidence, the body counts, the consistent field reports, and the objective temperature readings, slowly but surely eroded the wall of denial. The eventual official admission that the A14 regulator was fundamentally flawed marked a major turning point, not just for the oxygen crisis, but for the military's willingness to integrate field feedback into its design process. The crisis underscored the fact that testing conducted only under ideal controlled conditions is a direct path to military failure. Weapons and life support systems must be tested under the worst possible combat conditions to ensure reliability. The legacy of the A14 regulator is a testament to the moral courage of the few who fought against institutional inertia to save the lives of their comrades. The critical need to understand and resolve the regulator crisis led to the formation of dedicated, highly specialized testing teams. Unlike the initial, inadequate testing conducted by the ATSC, these new teams were tasked with replicating the precise, brutal conditions of the high-altitude European winter. A central requirement was the development of specialized cold chambers, massive, insulated rooms capable of sustaining temperatures below -60 degrees Fahrenheit for periods exceeding 10 hours, simulating a full combat mission. These chambers became the new front line of the engineering war. Within these chambers, engineers and volunteer crew members would meticulously test every component of the oxygen system, monitoring flow rates, pressure changes, and the exact points at which the critical valves failed due to freezing. The tests were physically demanding and dangerous, requiring the volunteers to wear full high-altitude gear and masks, risking real anoxia for the sake of scientific data. The investigations quickly confirmed the presence of the choke point within the A14 regulator, isolating the precise valve where moisture condensed and froze due to the rapid decompression and resulting temperature drop. This rigorous testing phase finally provided the hard, undeniable evidence needed to mandate a complete redesign of the A14 regulator. However, the solution required immediate implementation in the field, where hundreds of B-17s were already flying daily missions. The Air Corps developed an interim solution that could be applied immediately to existing A14 regulators. A specialized insulating cover, combined with a manual procedure for periodic drying and lubrication, designed to delay the freezing process. This quick fix was a necessary tactical measure, acknowledging the systemic flaw while the permanent solution was being developed and manufactured. The permanent fix involved a redesign of the valve seat to be less susceptible to moisture condensation and the integration of a small, internal heating element powered by the aircraft's electrical system. This heating element would maintain the critical valve components just above the freezing point, eliminating the potential for ice formation. This permanent solution, designated the Type A15 regulator, or later versions, represented a significant triumph for the field investigators and a massive, costly admission of failure by the original designers. The mass production and distribution of the new A15 regulators constituted a logistical challenge on a vast scale, requiring the retrofitting of thousands of aircraft across multiple theaters of war. The entire process, from initial reports of failure to final implementation of the permanent fix, spanned over a year marked by continued, avoidable losses. The saga of the A14 regulator became a grim, enduring case study in the perils of inadequate environmental testing in wartime procurement, emphasizing that in the high-altitude air war, engineering flaws were indistinguishable from enemy action. The eventual official admission of the A14's fatal flaw triggered a massive institutional pivot, focusing on systemic change to prevent future failures of similar magnitude. The Air Technical Service Command, ATSC, was forced to undertake a comprehensive review of all life support and environmental testing protocols. The core lesson was unambiguous. High-altitude equipment could no longer be certified based on testing done at ambient temperatures. This led to a significant, rapid investment in new, highly specialized environmental testing facilities capable of reliably replicating the extreme cold, low pressure, and humidity of the combat zone. These new facilities ensured that every component, from oxygen masks to electrical wiring, was certified to operate reliably under sustained operational stress. Furthermore, the crisis spurred a necessary shift in the organizational culture, particularly regarding the integration of field feedback. The experiences of the A14 crisis demonstrated that the most valuable data often originated not from the design engineers, but from the mechanics, gunners, and medical officers operating the equipment under fire. New reporting protocols were established to ensure that field complaints were immediately escalated and investigated by technical personnel, bypassing the defensive bureaucratic layers that had initially suppressed the truth. This institutional change was monumental, acknowledging that true engineering mastery required humility and an active willingness to learn from the chaotic reality of combat. Medical protocol also underwent a necessary revolution. Flight surgeons and medical officers were trained to recognize the subtle, creeping signs of anoxia in crews, often disguised as fatigue or mild confusion. New diagnostic equipment and procedures were implemented to monitor crew members more closely during high-altitude operations, treating oxygen deprivation not as a potential accident, but as a constant, ever-present threat. The crisis also brought crucial attention to the entire high-altitude equipment ecosystem. Investigators realized that the A14 regulator was merely the most lethal component of a system that included masks, hoses, and connectors, all of which were susceptible to freezing or failure. This holistic approach led to improvements in mask design to prevent rebreathing and icing, and the standardization of moisture-wicking materials throughout the entire oxygen supply chain. The saga of the B-17's silent killer served as a permanent, grim reminder that air superiority is not guaranteed solely by engine power and armament. It is built on the sustained, unflinching reliability of the life support systems that keep the airmen alive in the lethal, void-like environment they are forced to conquer. The lives lost were the ultimate, tragic cost of the lesson learned, ensuring that future generations of high-altitude flyers would benefit from the painful, meticulous after-action report derived from the A14 failure. The integration of the redesigned oxygen system, featuring the new A15 regulator with its anti-icing heating element, ushered in a necessary era of confidence for the 8th Air Force. However, the crisis left an indelible psychological scar on the airmen. The initial loss of faith in their own life support system created deep-seated anxieties that were difficult to eradicate, even after the permanent fix was implemented. The crews who had personally witnessed their comrades succumb to anoxia maintained a vigilant, almost obsessive focus on every flicker of the regulator's needle and every whisper of air within their masks. This constant vigilance, while born of fear, ultimately contributed to a safer operational environment, establishing a culture of personal responsibility for equipment function that extended far beyond the official maintenance checklist. The ordeal underscored the vulnerability of man against nature at extreme altitudes. The B-17, now flying with a reliable oxygen supply, continued its crucial role in destroying German industry. The reduction in unexplained casualties significantly boosted morale, validating the crew's initial reports and confirming that their fallen comrades were victims of a design flaw, not personal failure. The successful resolution of the crisis was a massive logistical feat, demanding the rapid production, distribution, and installation of thousands of new regulators across multiple continents. This massive retrofitting program was conducted in parallel with ongoing combat operations, highlighting the immense coordination required to sustain the air war. The A-14 crisis, by demanding such a high-level response, demonstrated the profound interconnectedness of engineering, logistics, and morale in modern warfare. Furthermore, the experience of the B-17 crews contributed directly to the safety protocols of other high-altitude aircraft. including the early jet fighters that were already beginning to operate at even higher, colder altitudes. The knowledge gained about moisture management, thermal integrity, and precise pressure regulation was immediately applicable to the next generation of aviation life support. The silent killer had been defeated, not by a technological miracle, but by the determined, methodical application of scientific investigation and engineering ingenuity. The eventual victory in the skies over Europe was fundamentally dependent on this microscopic fix, the small valve that ensured the breathing of the men who flew the heavy bombers. The after-action report on the A-14 regulator became a mandatory, somber lesson in every flight school, ensuring that the cost of learning this critical lesson would not be repeated by future generations of flyers. The saga of the B-17 oxygen crisis provided crucial insights that transcended the immediate problem of aviation life support, fundamentally influencing the design philosophy of the entire U.S. military. The institutional denial that initially stalled the solution highlighted the danger of technological arrogance. The belief that calculations made in a warm office are superior to the feedback from the cold, harsh realities of the combat zone. This realization led to the establishment of entirely new oversight bodies dedicated to ensuring operational realism in testing. The crisis also profoundly influenced the design philosophy regarding simplicity and redundancy. While the A-14 was a sophisticated piece of equipment, its complexity contained its flaw. The lessons learned emphasized the need for designs that were not only highly efficient, but also intrinsically robust and redundant, capable of surviving the loss of a single component or the intrusion of environmental variables like extreme cold. The principle of design for extreme environment became codified in military specifications, ensuring that future equipment was tested under a comprehensive matrix of realistic operational stresses rather than a limited set of ideal conditions. Furthermore, the sheer scale of the logistical challenge involved in retrofitting the entire bomber fleet underscored the importance of modular and accessible design. If the regulator had been easier to replace or repair in the field, the crisis could have been mitigated much faster. This realization contributed to the modern military emphasis on equipment maintenance, accessibility, and rapid, field-based repair capabilities. The most enduring legacy, however, is the ethical dimension of the crisis. The eventual admission of the flaw served as a stark, permanent reminder that the welfare and accurate reporting of the fighting personnel must always supersede institutional pride or budgetary constraints. The lives lost were the ultimate tragic cost of the lesson learned, a lesson that ensured future generations of airmen would have unwavering confidence in the equipment that formed their very lifeline. The resolution of the A-14 crisis was a quiet, internal victory, a bureaucratic and engineering triumph that secured the human element of the strategic air war. Without the reliable flow of oxygen, the B-17 would have been grounded, and the strategic bombing campaign over Europe would have been rendered ineffective. The small valve, ultimately, held the key to Allied air superiority. The successful resolution of the A-14 regulator crisis marked a crucial, yet often overlooked, strategic victory that directly enabled the sustained air superiority required to defeat the Axis powers. By late 1944 and early 1945, the heavy bomber fleet was finally operating with the confidence and reliability it should have possessed from the beginning. The B-17, flying with the dependable A-15 regulator, could now sustain the high-altitude formations necessary for mutual defense and accurate bombing runs, when weather permitted, reducing the vulnerability to German interceptors. The ability to complete missions without catastrophic internal failure meant fewer scrubbed sorties and a higher success rate for bombing objectives. This engineering triumph contributed directly to the systematic dismantling of the German war machine, crippling industrial output and logistical networks. The resolution of the crisis also had a profound impact on the operational deployment of American forces in other theaters. The lessons learned about thermal management and moisture control were immediately applied to equipment destined for the Arctic conditions of the North Pacific and the high-altitude challenges of the Himalayan hump route to China. The wisdom gained from the B-17 failures saved lives across the globe. The saga itself became a mandatory case study in the new military academies, embodying the principle that technological advancement is meaningless without operational reliability. Future engineering programs, from the development of modern fighter jets to astronaut life support systems, were built upon the protocols established in the wake of the A-14 flaw, protocols demanding rigorous environmental stress testing. The crisis fundamentally changed the conversation between the engineers and the users. No longer could a design be signed off based purely on theoretical modeling. It had to withstand the ultimate test of the environment. The sacrifice of the early bomber crews provided the necessary, tragic data that fueled this institutional revolution. The legacy of the silent killer is the creation of a safer, more reliable military procurement system, one that respects the severity of the operational environment and the critical importance of every single component that ensures the survival of the fighting man. The B-17's oxygen secret, once exposed, fortified the very foundation of the modern U.S. Air Force. The final after-action report on the B-17's oxygen crisis offers a stark and enduring lesson in the relationship between man, machine, and the environment. The tragedy was ultimately a confrontation between the rigid, predictable world of engineering theory and the chaotic, unforgiving reality of combat thermodynamics. The fatal flaw, a microscopic accumulation of frozen moisture within a delicate valve, was a problem of complexity and context. Overlooked because the initial testing failed to grasp the full, sustained severity of the high-altitude environment. The cost of this oversight was devastating, measured in the avoidable losses of highly skilled airmen and the immense delay imposed upon the strategic bombing campaign. The eventual resolution, the implementation of the A-15 regulator with its crucial heating element, was a triumph not of new science, but of application. The triumph of practical, field-derived evidence over institutional denial. The lives lost were the ultimate, tragic data points that forced the hand of bureaucracy. The profound legacy of the crisis is the permanent embedding of the extreme environment testing philosophy within military procurement. The B-17's silent killer ensures that every subsequent life support system, every cockpit component, and every high-altitude platform is certified under conditions that exceed those encountered in combat. The story reinforces the ethical imperative that the welfare of the fighting force must always supersede budgetary concerns or engineering pride. The B-17 Flying Fortress, a machine famed for its endurance and firepower, found its true test not against the Luftwaffe, but against the simple, inexorable laws of physics. The crew's ultimate victory was achieved not just by fighting the enemy, but by understanding and finally conquering the lethal environment they operated in. The A-14 regulator, now a relic of history, stands as a permanent reminder that in modern warfare, the reliability of the oxygen valve is as strategically important as the firepower of the machine guns. This remains the critical lesson of the final after-action report. The strongest links in the military chain are often the smallest, most meticulously tested components of the system.